me of an old joke. What was the penalty of the rainbow? It was sent to prison. It was a light sentence, but it got some time to reflect. So tell us about rainbow cycle numbers.
Okay. Thank you, Moshe. Yeah, so maybe from the title itself, you think what has this topic to do in this workshop. So here that's okay, but that's kind of the outline. That's the different topics I want to discuss, and they are connected. So first, I will start with fair allocation of goods. I think it's an important topic of computational social choice. And then we will see that for the existence of certain allocations, this so-called rainbow cycle number is important. That's from extremal combinatorics, a number associated to certain graphs. And when you can compute this rainbow cycling number, then you get kind of better fair allocations. And then we see that actually computing this rainbow cycling number is quite a challenging question. And we will use, I will show you how our method of SAT modulo symmetries can be applied to this, and how we can compute rainbow cycle numbers, at least for like small rainbow cycle numbers. But let's start with the beginning. What's the problem setting? Fair allocation of goods. So we have n agents, and we have a set M of goods. And now we want to allocate this. So here, this is our running example. It's a very trivial example. We have Alice and Bob, and we have the goods are a house, a laptop, and a paperclip. And so what each agent I will receive a subset capital AI of the set of goods. And yeah, the same good can't be allocated to two different agents. And we also want to allocate all the goods. So we will also discuss later partial allocations where we can donate some of the goods to charity, which is actually a very easy escape route to make it fair. Exactly. But that's the, as I said, that's the trivial solution, but also very important, we have evaluation function, or actually we have, for each agent I, we have an evaluation function which gives each subset of the set M of goods a real number. It basically measures how well the agent likes this subset. And here we have an example of this valuation numbers, but this is a very special case because here both agents have exactly the same valuation, which in general is not necessarily true. And here it's also additive because basically each item has a different kind of worth, and the subset is just the sum of the worth of its items. But in general, that's not necessarily true. Like think it's a house and the garage. You want to get the house together with the garage and not the two things separate. Okay, then envy-freeness. So envy-freeness is defined as that for any two agents I and j, agent I kind of prefers the goods he or she receives at least as high as the goods received by agent j. And this is kind of would be the ideal solution. So if we could find an allocation which is envy-free, then basically we are pretty happy. But already in our trivial example, such an allocation doesn't exist. Because whenever the agent who receives the house, the other agent will envy. Because even if they got both the paperclip and the laptop. Therefore, people have considered relaxations of this strong requirement of envy-freeness. And there are two in particular: one, envy-free up to one good, and envy-free up to any good. So here we allow, here in this inequality that we had for envy-freeness, we allow to remove one good from the allocation of the other agent, and then the envy basically goes away. But the difference here is that for EF1, we can remove just a particular good from this allocation. Let's say we remove the most valuable good, whereas for EFX, this must hold for any good. So even if we remove kind of the least valuable good, the envy should disappear. Yes, I think there's some, in the definitions I didn't find it, but I think it's very reasonable to assume some monotonicity requirements. Second? Yeah, if it's additive, then it's monotone, yes. No, I don't assume additivity. That's just a special case. But in this example, we have additivity. And so here we see this allocation where Alice gets the house and the paperclip, Bob gets the laptop. It's EF1 because when we remove the house from this allocation, then the envy disappears. But it's not EFX because for EFX, if we just would remove the paperclip from the allocation to Alice, Bob would still envy her. But this here is an EFX because now there's only one good one could remove from this allocation, and that's the house, and so this would be EFX. Of course, as Moshe already pointed out, if we allow partial allocations, we can just send everything to charity, then of course there exists always an envy-free allocation. But I think in the field, one of the most significant open questions is whether an EFX always exists. So it's actually quite remarkable that it could not have, it wasn't proven. EFX.
Is envy-free?
Up to any.
Up to any.
So envy-freeness is any good. So that's kind of the stronger of the two variants. So I think EF1 exists, but EFX is open whether it always exists. And there have been special cases for which it has been shown. For instance, if there are only two agents, then there exists always an envy-free X allocation. And if we have three agents and we have additive valuations. So I think the kind of the first open case would be 4 agents and additive valuations. But now people also, because this seems to be very hard nut to crack, people looked at further relaxations. And one of them is approximative EFX. So here the definition is the same as before, but here we have some factor alpha, and basically our inequality here can be kind of weakened with this alpha, which is like a 1 minus epsilon parameter. Yes?
You have EFX and you have EF1.
Yeah.
There is in between EF2, EF3.
I guess one can also define others, yeah. But EF1 will also not play a big role further on in my talk. So this...
If you want, for example, if one exists, right? Mm-hmm. You want EF1 and optimal societal optimum?
I guess, I think the literature is here quite broad. People have studied very many variants. And so I'm also, in the next slide, I will have a look at this variant with where we minimize the goods that go to charity. Okay. And this is actually now the link to the rainbow color number. Before I show you the theorem that links these two concepts, what is the rainbow cycling number? So you look at a k-partite graph where each block has d elements, and it's a directed graph, and it has the property that every vertex has an incoming edge from all the other blocks. And there should not be a rainbow cycle. A rainbow cycle is a cycle where every color, so meaning every block, appears at most once on the cycle. And now this rainbow cycle number is the largest integer k, such that there exists such a k-partite graph. So you fix basically the size of the blocks, and you want to get the largest number of blocks with this property. Yes?
You're not fixing the graph here?
You're not fixing the graph. It's basically the rainbow cycle number is the largest integer k, such that there exists a k-partite directed graph with this property. Therefore, it's also difficult to compute it, because the only thing that you know about it is d and k, like when you try to compute the number. And for d and k, there are many different graphs that you need to check.
Won't make it easier because you can build your graph. Wouldn't this fact make it easier to compute? Because you can make, since you can build your graph, you can take the graph and build as you need it, or? So my intuition is that if you can build your graph as you want, the problem will become easier.
The problem is at a certain stage, when you add many of these blocks, you will generate rainbow cycles. So it's like often in extremal combinatorics, you have two conflicting objectives. One is you want to make the graph as large as possible, but on the other hand, you want to avoid these rainbow cycles. And that makes it difficult to compute.
Because you want to avoid the rainbow cycle.
You want to avoid it, yes.
Okay, I see. Now I see. Thank you.
Is there an explicit upper bound?
Yes, on the next slide.
Okay.
Yeah, so it's about computing rainbow cycle number, but sorry, and then slide after the next slide. Here, just to not lose the chain of thought, this is now the connection with the alpha EFX. So, okay, maybe this the technical statement of the theorem is difficult to parse, but it basically says that based on the rainbow cycle number, one gets 1 minus epsilon EFX allocations with a sublinear number of unallocated items. So you can basically, if you have small rainbow cycle numbers, then you get a small number of unallocated items. It guarantees. It guarantees, but there also exists an algorithmic version of this that you can also compute it. Okay, now the bounds. There is the rainbow cycle number d is at least d itself. But the upper bound is quite large, d to the 4 plus d. And yeah, in the paper where this was introduced, they also, of course, said that it would be very interesting to compute this number. And for small values, it's known, like for R2 and so for d equals 2 and d equals 3, the lower bound is actually matched by the upper bound. But already for d equals 4, it's open. And kind of the technical contribution of this talk is trying to compute this. To minimize.
Why minimize the number of unallocateds?
Yeah, because when you allow to donate everything to charity, then the problem trivializes.
No, I understand, but just the objective to optimize for. So why is it the number of items rather than the value of the unallocated items?
I guess one could also study this more refined by weighting the value of the unallocated items. Yeah, I think it's a fair comment. And but basically, yeah, I also didn't invent it. So that's apparently in computational social choice, that's what people have been studying.
But there is no value. Right. So if I understand correctly, there is no value because each person has a value for a set. So you can't even give.
Yeah, one could. Yeah, one could discuss how to do this, taking the minimum overall agents, or but in the literature they studied just minimizing the number of unallocated items. Okay, and now it's quite challenging because we will see. Everything can be solved by exhaustive search, but we meet, for instance, a standard way of doing this would be to use the good old tool Naughty from Brennan McKay. That's a very nice and useful software package where you can enumerate graphs up to a certain number of vertices, isomorph-free. So the important thing here, you don't want to look at the same graph with different isomorphic copies again and again. However, already like when you want to solve this case with d equals 4, the number of vertices is 20. And when you look at the online encyclopedia of integer sequence, only listed up to 19 vertices, and already there the number is quite large. One can do also Naughty, to be fair, Naughty one can also do some degree constraints, and one can make it a little bit more efficient, but still generate and test, like generate all possible graphs and check for each of them whether it contains a rainbow cycle is not feasible. So therefore, it would be nice to generate only graphs without rainbow cycles, to already, in the generation process, already take into consideration the properties that we want to have. And that leads us to the graph search problem as a synthesis problem. Because we actually want to synthesize a graph that satisfies certain properties. And so, yeah, it's a synthesis problem. And we can also do it like in a propositional setting where like when we fix the number n of vertices, and for each edge, we introduce a propositional variable, which can be true or false, and which says whether this edge exists or doesn't exist in the graph. And now, a very natural thing would be you just write down a propositional encoding of your properties, send this to a SAT solver, and wait for the result. But as I said, it's very important to break symmetries. And we want to do an isomorph-free generation. Like, for instance, this graph, 5 vertices, has 120 different isomorphic copies if we keep the vertices numbered 1 to 5. And only one of them should be declared as the canonical one. Like that's the typical thing you do. You have an isomorphism class, and you have some canonicity function alpha that declares basically, that maps only one of these graphs to itself. And that's now your canonical object in this set. And there are different ways of defining canonicity. A very popular one, and for in our context, very useful one, is you look at the adjacency matrix and you concatenate all the the rows to a long vector, and then you take lexicographic ordering. And now among all these 120 graphs, one of them will be lexicographically minimal, and then you just say, this is my canonical object. Okay, so easy. We just now, in our SAT encoding, we take the property we are looking for, and we also add canonicity. It should be minimal with respect to this lexicographical ordering. However, there's a caveat that it's not known how to encode in polynomial space the property of being canonical. And therefore, a few years ago, we came up with this system, SAT modulo symmetries, which, if you know SAT modulo theory, so we take a similar approach. So we have the SAT solver. We also encode our property as usual. But then whenever an edge variable is decided, then we have something that we call a partially defined graph. So now for some edges, we now know they are there. For some, we know they are absent. But here, these dotted edges, we don't know yet. Therefore, it's partially defined. Then we send this partially defined graph to a special algorithm which checks whether this partially defined graph can be made canonical. And if not, we learn a clause and send it back to the solver. And now I will spend maybe 2 minutes on how we do this, because for the SMS system, that's kind of the key thing why it works so well. And we have now quite a number of applications where we could improve known bounds with it. And I think it's interesting on its own. We have this partially defined graph, and XP is the set of all fully defined graphs that this partially defined graph can be extended to. So there are 3 unknown edges, so therefore we have 8 fully defined graphs. And so the kind of the ideal definition would be, we say this partially defined graph is non-canonical if neither of these fully defined graphs is canonical. So this would be that for each of these fully defined graphs, there exists a permutation that makes the permuted graph smaller than the graph itself, which means G is not canonical. However, this non-canonicity test, we have to do thousands of times each second. So this needs to be very fast. And so this is not feasible. This would take far, far too long. And so we settled on the following. We call this certified non-canonical. There's a subtle change. We basically swap the quantifier, the permutation, existence of the permutation, and all graphs G in the set XP. We say there exists a permutation such that for all graphs in the set XP, applying this permutation gives us a lexicographically smaller graph. And this happens to be still quite powerful in our search, and is also, we have a special constraint propagation algorithm to compute this, so we can do this very fast. And the nice thing is that we can, for each clause that we learn, we can keep by this permutation as some kind of a certificate to later on, if we want to check whether the computation was correct, we can later simply check whether this permutation really was the certificate for non-canonicity. Okay, so here back to this diagram.
Can you go back 1 slide?
Mm-hmm.
No, the one with the certificate. So I'm not quite sure why you have, what do you gain having the certificate?
That's because we want to produce a DRAD proof at the end. And
but now you have this extra work on every step to computing certificates.
Yes.
That's a lot of extra work.
No, it's not extra work, because when we find non-canonicity, when this
you find a
special algorithm
permutation.
finds
You find
it,
a permutation.
we have by anyway.
I see. You just
So
save it. You
We
just
just save it.
I
No,
see.
no extra
Okay.
work.
Okay. Got you.
Okay, so we store the certificate, and now for our problem, the rainbow cycle number. So here for the sub encoding, that every vertex has an incoming edge from each other block, we can express, because this is an existential property, that's kind of an NP property. But the non-existence of a rainbow cycle, encoding it here would blow up. It's a huge encoding size. So therefore, we have another subsolver which checks the negation of the NP property. So whenever we get the solution here, we call this other subsolver which looks for a rainbow cycle. And if it finds one, it learns a clause and sends it back to the kind of the main subsolver. So this called co-certificate learning, and we have already used this in other contexts, because many problems people are interested in have this combination of an NP property together with a co-NP property. And now time is running out, so I have to speed up a bit. Now the results. So for verifying that rainbow cycle number of 3 equals 3, we need to show that this is unsatisfiable, and we can do this within a second. For the open case that we solved now, that the number of 4 is 4, we can solve in 23 minutes. And unfortunately, the next iteration times out. But we have... Yeah, we still wanted to improve it, and that's actually, it's a paper that will be presented at the SAT conference. Kind of the really new thing here is, I would say, is invariant pruning, where we basically take an invariant of the graph and we fix this invariant. And I now unfortunately have to skip over these details, but this basically we apply the encoding over and over again, and we can refine a certain invariant. In our case here, the maximum integrity of the graph, and this way we can kind of make the problem easier and easier. And indeed, with invariant pruning, what we took 23 seconds. Now we can, 23 minutes, we now could show in half a minute. So we got here quite a significant speed up. Not that the 23 minutes were too long, but it was the hope that for the next iteration, it's better. We could at least improve this bound on the integrity, but still showing it timed out, and of course maybe throwing a ton of computation power on it might still lead us somewhere. Yeah, here very quickly, just these proofs. Why do we store these certificates? Because at the end we want to generate a proof that can be checked by a third party. And in the SAT solving community, kind of a golden standard are the so-called DRAT proofs. So most SAT solvers can directly produce these certificates, and there also exists very lightweight proof checker for this format. But now, in addition to our encoding, we also have additional clauses, the clauses from the canonicity, but we just add them as additional axioms, and then we can actually run a SAT solver again without all this propagation, just on this extended set of axioms, and we get the DRAT proof. And the same holds also for the co-certificate learning. The things when the second SAT solver says that there exists a rainbow cycle, we learn a clause, and also here we just memorize the satisfying assignment, and so we can also certify the clauses, and altogether we can send to a solver to produce a direct proof. Okay, summing up this third division of goods, EFX, yeah, one can discuss whether EFX is kind of the best thing in the field, but apparently people in computational social choice seem to like the EFX allocation variant. The theorem I showed gives a connection between rainbow cycle numbers and approximate EFX. Then I showed you how we compute rainbow cycle numbers with SAT modulo symmetries, and we could determine the force of the numbers, and we can certify it with a direct proof. And yeah, here just very quickly, these are some of our results that we could achieve with SAT modulo symmetries. So we are not just on graphs, we also have Chaudhury sums on smallest unsatisfiable formulas. We have something on matrices, so it's can also be applied beyond graphs. And these are the resources. There's also the documentation on SAT modulo symmetries. And actually, a year ago at this very place, I gave a talk on SAT modulo symmetries. So when you want to hear a little bit more details on the system, please check out this talk. Thank you.
The issue that didn't come up here is the total utility. And I would think that we would like to find an allocation that is socially optimal and envy-free under some of this definition. So how hard it is to find such an allocation? Socially optimal means I just take the sum of all the utilities. I want to maximize that.
Yeah, I guess here people were really looking at avoiding envy. It's similar, I would guess, so I'm not an expert in computational social choice, but for instance, when you, the Gale-Shapley algorithm for stable matchings.
Yeah.
It does not optimize like for each of the two parties to get the optimal partner, but it just avoids unstable pairs. And yeah. I would assume that here the situation is similar. But of course, one can also refine it, maybe to also take into account the common social good or things like that.
I mean, stable matching is because we don't really have obvious quantity to optimize other than, you know, the no switching condition.
Yeah.
But here we have a utility. I mean, the problem is defined by a utility function. So it seems obvious to take the sum and to say this is the the societal utility and try to optimize.
I guess particular, maybe people have already looked into that. For those cases where we already know that an EFX exists, I guess one can now, on top of the plain existence, also look into optimizing various things.
Yeah.
By the way, there is also an interesting thing about if the goods are divisible, then the problem is solved. Actually, has been studied almost 100 years ago. And for instance, the solution for the two agents is very simple. You ask the first agent to divide the goods into two
it's a cake.
parts,
it's a cake division. It's a cake division.
The same value for the agent, and the other agent can choose between the two.
Yeah.
Right. I was wondering about the, in some way, robustness of the connection, in the sense that if the preferences of the agents change in some small way, define small as you like, is there a small change in the color problem, that in the solution that you get there, that you can make, so without computing the whole thing from the start to find a new solution for new preferences? So is there something of this sort that you could do, that just small change on the solution?
So that I don't know from the top of my head. I don't know whether, but it's a very interesting question.
It's a sensible question.
It's an interesting question, but I don't know whether this has been studied.
This is something that we're looking at with EF1 and round robin sort of thing with a student of mine, and I was just thinking this is sensible here as well, and it uses the machinery. I don't know, but it's very interesting.
Yeah, but robustness, I certainly agree that it's an interesting point that one could put into the equation.
Ask question on behalf of Supratic, which says like, does the connection of alpha EFX to rainbow number also work for non-additive value functions? Okay, Supratic, you've certainly seen the answer. Okay, thank you.
By the way, I made a mistake. This will appear at CP, not at SAT.
I have a quick question about the SMS thing, right?
Mm-hmm.
So I was like, at some point I was looking at different encoding of formulas for enforcing this kind of canonicity. I think there was some kind of formula that was doing this kind of experiments. And because like you can enforce this thing as well in the formula, but I think you're kind of doing this kind of outside, right? This, the canonicity or you.
Yes, yes.
So the experiments will be much better, I presume, like than just enforcing this directly in the formula, because I tried this different kind of encoding, it usually didn't work.
Yeah,
out,
no,
so.
it's a good question.
Yeah.
So people will want, if you sacrifice the full symmetry breaking, if you only say, for instance, swapping two vertices should not get you a lexicographically smaller graph, then this can be expressed. And people like Kodish et al. They tried this. But if you want to do like a full symmetry breaking, then it's not known how to encode this with a polynomial number of clauses in a formula. And we also very recently tried, in principle, because it's actually a QBF problem. In QBF, you can give a polynomial encoding. And so we encoded this minimality into QBF, but that didn't work at all. So we have now also a variant with QBF, where instead of the second SAT solver, we can actually express the whole property, like a p-space property directly, and SMS will still work with it using a QBF solver, but the minimality check, this canonicity check, is still done externally by our external propagator.
I wanted to ask a high-level question about symmetry in SAT solving. You know, that famous puzzle with the chess board and the two corners missing. The solution, I mean, it seems like that's another obvious place that you can apply symmetry, but at least if I remember, the solution that usually is presented is not actually using symmetry. It's this kind of learn that if this is not a satisfying assignment, all these others are also not a satisfying assignment. I was just wondering, is there a fundamental difference in the view, the way you do it and the way that happens? Or no, they're fundamentally the same thing?
Yeah, I think it's a bit different. It is if you, because there you still have like one instance and you want to break symmetries in the solutions. But here we have this, we have this object. So here, you're for this puzzle, you are given the object, but here we're looking for the object. And so it's...
But there the object is the tiling, right? I just want to prove that a tiling doesn't exist. And you want to prove that a loop-free graph doesn't exist. So...
Yeah, on a very high level, these two problems are very similar, yeah. But I think in practice, it would the different techniques would apply, because for this puzzle problem, you would just maybe come up with a symmetry breaking by hand, so to speak, and just add some symmetry breaking clauses that take care of the symmetries. Whereas for the problems we study here, the possible symmetries are basically there's an exponential number of possible symmetries, because you don't know what the object you will finally compute will look like.